Alrighty, hello and good afternoon. Welcome to Monday. Monday. I almost said Monday morning lecture. It's 1 o'clock. So to Monday afternoon lecture. Just by way of reminder. Veterans Day. So today's the 11th. No, today's the 9th. Wednesday, the 11th, is Veterans Day, 11th of November. So we will not have class on Wednesday. So this will be a one-stream week, both for lecture and office hours later tonight. So we're going to continue our discussion of Lewis structures. So our discussion of Lewis theory, and we left on Wednesday talking about how to draw the Lewis dot structures of atoms, right, of elements, and we said that Lewis theory, our discussion of Lewis theory, will be restricted to the main group elements, and that you could determine the number of dots, the number of valence electrons for a main group element, based on its position, the column that it falls in the main group. You can go back and see Wednesday's lecture if you'd like a review of that. Now, hey Kate, how's it going? So we are going to, our focus for today is Lewis theory, as I presented it on Wednesday. It was another way of depicting the number of valence electrons in a molecule. But the point of Lewis theory is to move beyond, I said the number of valence electrons in a molecule. I meant to say the number of valence electrons in an atom, right? We were looking at it as just another way to write the valence electrons in an atom, like electron configurations or orbital diagrams, all right? Today we're going to expand beyond our view of just the atom to looking at entire molecules, all right? We're going to talk about how the structure of molecules, and we're going to look at ionic compounds and then covalent compounds, and the difference. So we know there's a difference between ionic and covalent compounds, right? We've learned how to name each, but the fundamental difference on a very, very fundamental level, fundamental difference between ionic compounds and covalent compounds are the types of bonds they form, all right? There we go. For ionic bonds, when we're talking about ionic bonds, in ionic bonds, electrons are taken by the more electronegative atom from the less electronegative atom. All right, so when we talk about ionic bonds, we're talking about electrons being taken. And for covalent bonds, electrons are shared between atoms. So with ionic bonds, it's very competitive. The more electronegative element will take electrons away from the less electronegative element. And for covalent bonds, it's more of a constructive, it's more of a cooperative environment where they share electrons between the two atoms, all right? Now, and this was alluded to when we wrote out the definition of an ionic bond. What determines whether or not your bond ends up being covalent versus ionic is electronegativity. Specifically, it is the difference in electronegativity between two atoms that will determine if one will steal from the other, forming an ionic bond, or if the electrons will be shared, forming a covalent bond. All right? And so, when we look at... So I'm going to be writing this quite a bit, especially towards the end, once we start talking about intermolecular forces. So this is the difference in electronegativity All right, that's En stands for electronegativity. That delta is difference. All right, and the difference in electronegativity between two atoms, to calculate it, you simply take the more electronegative atom. You take the more electronegative atom's electronegativity and subtract the less electronegative atom's electronegativity. All right, so that's how you calculate the difference. And the difference between the electronegativities of two atoms that are bonding together will determine the type of bond that they make. So, for example, if the difference in electronegativity between two atoms is 0.4 or lower, then we would say that that bond is covalent. Right, we're making a chart here. If the difference in electronegativity between two atoms is 0.4 or lower, we call it a covalent bond. If the difference in electronegativity between two atoms is 2.0 or higher, then those two atoms form an ionic bond. All right? And if, so you may be going, okay, 0.4 or lower, covalent, 2.0 and higher, ionic. What happens when the difference in electronegativity lies in between 0.5 to 2.0? In this instance, if it's in between there, it forms a special type of covalent bond that's called polar covalent. All right, we will spend a lot more time talking about polar covalent bonds later, once we're done discussing Vesper theory, so that'll come back later. But I wanted to introduce the idea of electronegativity now, because we're about to start talking about we're about to start talking about ionic Lewis structures for ionic compounds, as opposed to Lewis structures for covalent compounds. So the way you determine whether or not you're ionic or covalent is by looking at the difference in electronegativity. And again, we'll be spending a lot more time with this in the future. For now, let's go ahead and dive in to talking about ionic Lewis structures. All right, ionic Lewis structures. Now, I think a great place to start is sodium chloride. So let's look at the Lewis structure for table salts. All right. Well, if you look at the periodic table, sodium is in column 1. All right. So sodium will have, or actually, because it's in the first column of the periodic table, that means its Lewis structure has one dot, right? One valence electron. And if you look at chlorine, chlorine is in the 7th column on the periodic table. So that means the Lewis structure for chlorine is 7. 1, 2, 3, 4, 5, 6, 7. So that is the Lewis dot structure for sodium atoms and for chlorine atoms, all right, kind of discretely. Now, when you look at the electronegativities for sodium and chlorine, so let's scoot this over a little bit. So when you look at your electronegativity numbers, sodium's electronegativity is 0.9 and chlorine's electronegativity is 3.0. Now, electronegativity numbers are not something you need to memorize. I'll provide them for you when you need them, just as I did here. So because chlorine is more electronegative than sodium, all right, and we're dealing with an ionic compound, right, because the difference in electronegativity is 3.0 minus 0.9, so this is 2.1, right, which makes this ionic. We know that chlorine is going to take electrons forcibly from sodium to form this ionic bond. Now let's talk about how this actually happens, right? How this physically shakes down, all right? How does a molecule of sodium chloride form? Well, as we already said, chlorine is more electronegative. So chlorine is going to grab sodium's electron and steal it. All right. After chlorine takes sodium's electron, you'll notice that it goes from having 7 valence electrons to 8. All right. 8 valence electrons. Also, another thing that happens is it's gained 1 negative charge, but the number of protons have stayed the same. So chlorine now becomes an ion. Chloride, it has a charge of -1. Sodium lost a negative charge, and so it has, but its number of protons stayed the same, so now it has a positive charge. So now we have a sodium cation and a chloride anion, all right? And this is the Lewis structure for the molecule sodium chloride, all right? Couple things. You may be looking at this structure and thinking, well, where's the bond? Because you've seen drawings of molecules, and bonds are usually these little lines that connect all the atoms together, and you're looking at this going, there's no bond. Where's the ionic bond? Now, remember, those lines that you're used to seeing, we'll get to those when we talk about covalent compounds, all right? Those lines represent 2 electrons being shared between 2 nuclei, but in ionic compounds, electrons aren't shared. The ionic bond is actually the attraction between the positive and negative charges of the 2 ions. The ionic bond is the attraction between opposite charges. All right, it is the attraction between the positive and negative charge for the sodium cation and chloride anion. So you don't see anything physically connecting them, but they're stuck together because that negative and positive charge are each drawn to the other. All right, so that's where the ionic bond is in this molecule. A second thing that I want to say is, and this is just worth noting, that ionic bonds are stronger than covalent bonds. I think it's easy to think of covalent bonds as being very strong things, which they are, because you see them physically attached. But ionic bonds, the attraction between that positive and negative are actually, it's a stronger thing than covalent bonds. So that's something worth knowing. All right. Now you may look at this and think, okay, that's all well and good. That is so this right here, this is the Lewis structure for sodium chloride. But you may be wondering why. All right. Why does sodium want to lose an electron? Why does chlorine want to gain an electron? And the answer to that question of why. All right, so let's stop for a moment and ask, why does this even happen? All right, and I'm going to redraw my Lewis structure for sodium chloride like I had on the previous page. The answer to why has to do with the noble gases, right? Sodium, we know that the noble gases, that last column on the periodic table, are not compounds, atoms are super stable, right? They are super stable. And sodium wants to lose one electron so it can have the same electron configuration as neon, its nearest noble gas. Chlorine wants to gain an electron so it can have the same electron configuration as argon. So that's the reason why sodium loses and chlorine gains, is because they each want the stability of that noble gas configuration. All right. And that noble gas configuration, right, the valence electrons for the noble gases are the source of their stability. And if you write out the electron configurations for all of them, you'll start to notice something interesting. All right. Helium's noble gas configuration is 1s2. Neon's is helium core 2s2, 2p6. Argon's helium core, sorry, not helium, neon. 3s2, 3p6. Krypton has an argon core. 4s2, 3d10, 4p6. Xenon has a krypton core. 5s2, 4d10, 5p6. Radon has a xenon core, 6s2, 5d10, 4f14, 6p6, and then magnesium, radon core, 7s2, 6d10, 5f14, 7p6. When you look at the highest energy shell for your noble gases, for neon, it's the second energy level. You've got 6 valence electrons. How about 6 plus 2? 8 valence electrons. If you look at argon, it's the third energy level, third shell. 8 valence electrons. If you look at krypton, if you look at the highest energy shell, which is the fourth shell, 8 valence electrons. Xenon, the highest energy shell, is the fifth shell, 8 valence electrons. We're lapping ourselves in color. Radon, the highest energy shell, is the sixth shell, 8 valence electrons. For magnesium, the highest energy shell is the seventh shell. All the noble gases have 8 valence electrons in their highest energy shell, which is what leads us to something called the octet rule. The octet rule. Now, you may be going, hang on, wait 1 second. One of these things is not like the other. What about helium? Helium only has 2 valence electrons. Well, helium will be the exception to the octet rule. The octet rule states that every main group element wants to have the same number of electrons as their nearest noble gas. And you must, in your Lewis structure for your molecule, make sure that every atom meets the octet rule. Now, almost 100% of the time, that the number of valence electrons of the nearest noble gas will be 8, because as you can see, every single element on the periodic table except for helium, every single noble gas on the periodic table except for helium has 8 valence electrons. It should be noted, however, that helium only has 2 valence electrons. So, for example, if you look at the element hydrogen, hydrogen will only want to gain 1 electron because its nearest noble gas is helium, or lithium will only want to lose 1 electron because its nearest noble gas is helium. So for those elements that are close to helium on the periodic table, they'll want to max out at 2, but everything else wants 8 because for every other element that is not closer to helium, they all want to be like their nearest noble gas, which all have 8 valence electrons. All right, so that's why it's called the octet rule. Okay, so with all that in mind, let's take a look and do another example with ionic Lewis structures. All right, so let's take a look at let's take a look at calcium chloride. Let's draw the Lewis structure for calcium chloride. All right. Well, let's start by looking at calcium has an electronegativity of 1.0. Chlorine has an electronegativity of 3.0. So our electronegativity difference here will be 3.0 minus 1.0. Oh wait, hang on. We're going to do, instead of calcium, we're going to do barium. All right, barium's electronegativity is 0.9. The reason why I had to change it is because technically calcium chloride does not form an ionic bond according to electronegativity. So this comes out to be, our difference in electronegativity is 2.1, which makes this an ionic bond. All right, so let's go ahead and take a look at barium on the periodic table. It's right here. It is in the second column, so it will have 2 valence electrons, which means its Lewis structure has 2 dots. All right, and when you look at chlorine, it is in the 7th column, so the Lewis structure for chlorine will have 7 dots. So 1, 2, 3, 4, 5, 6, and 7. All right. Now we know when we're dealing with ionic compounds that the more electronegative element steals an electron from the less electronegative element. All right. And so we have chlorine taking an electron from barium. Now, when barium loses an electron, its number of protons don't change, so it lost a negative charge, and so it has a positive charge left in the wake of losing that negative charge. Now, chlorine has gained an electron from barium, so it has now gained 1 electron. It has a negative charge. It is an anion, chloride. But you'll notice that chlorine has achieved its desired noble gas configuration, right? It wants to gain 1 electron to be like argon. But if you look at barium, barium's nearest noble gas with fewer electrons is xenon, and barium needs to lose 2 electrons. The problem is chloride isn't going to take a second electron. It's achieved its octet rule. It's content. Nothing else is going to happen. And so for barium to reach its octet rule, it has to react with a second atom of chlorine. Another chlorine atom needs to roll up and take that electron from barium. When it does, now barium has lost 2 negative charges, right? So we have our first chloride hanging out with its charge of -1. But now we have a second atom of chlorine that has taken an electron from barium, which picks up its own. The second atom of chlorine is now a second ion of chloride. And this is the Lewis structure for barium chloride. All right. And the reason why it will always form, remember way back at the beginning of this semester, we said that ionic compounds always form in the same ratio. The reason why that is because chlorine will always and only want to gain one electron. Barium will always want to lose two. And so barium will always need to react with one barium will always need to react with two chlorines in order for everyone to satisfy their octet rule. All right, so we're kind of getting a glimpse for the reason why we do things the way we do, right? We're kind of seeing the deeper cause here. All right, now, let's talk about, so that's ionic compounds. They're fairly straightforward. You have your less electronegative element that you're just trying to lose all its valence electrons, and you will react it with as many of the more electronegative element as you need to eat up all of those ions till everybody, all those electrons till everybody has their desired octet rule met. Let's go ahead and transition to covalent Lewis structures. All right. Now, we already said with covalent bonds that the electrons are shared, right? Not taken. They're shared and not taken. Now, that means that the way these molecules form will be fundamentally different than what we saw for ionic compounds. All right. So let's go ahead and we're going to start as simply as we can with H2. All right, now rolling in with our periodic table, you can see that hydrogen, so in the first column, it has one valence electron. So we have two hydrogen atoms, each with one valence electron. All right, two hydrogen atoms with each with one valence electron. Now, the problem here with ionic compounds, we knew that the more electronegative element is going to steal an electron, right? The problem here is that hydrogen has the same electronegativity as another hydrogen molecule, right? Neither is strong enough to take an electron forcibly from the other. So to achieve the octet rule, right, to have the same number of electrons as helium, there has to be a fundamentally different way of achieving that condition, all right? And what happens is the two hydrogen atoms move closer together, all right? They move together so that the orbital with each electron overlaps with the other. They get close enough so that they can share their electrons. Now, here's the deal. The two nuclei move together, so you have the electrons sandwiched in between, all right? Now, here's what happens. When you look at this situation, if you completely black out this hydrogen and just look at the blue hydrogen, it has access to two electrons. This blue hydrogen has access to two electrons. All right? If you completely black out the blue hydrogen and look exclusively at the red one, the red one also has access to two electrons. And because each of these atoms have access to the same number of electrons as helium, we say that the octet rule for each has been fulfilled, all right? Because both atoms have access to the number of electrons they need to attain that stability that helium enjoys on its own. Now, these two electrons, these two shared electrons are a covalent bond. These are a covalent bond. All right? That is what a covalent bond is. It's two electrons being shared as one nucleus. And it's never depicted as two dots in between two atoms. All right? So the way that you write the Lewis structure, draw the Lewis structure, for some people, I've run into this in high school. They're like, we drew Lewis structures where the covalent bonds were drawn as dots. Nobody draws them that way outside of high school. So the way you show a covalent bond properly is with a line between the two nuclei, all right? That line is a covalent bond. It represents two electrons, and it is the thing that is holding those two together, all right? That is a covalent bond, and this is the Lewis structure for H2. All right. So that is the Lewis structure for hydrogen. Let's do a slightly more complex Lewis structure. All right. Let's draw the Lewis structure for H2. No, we just did H2. How about H2O? Let's draw the Lewis structure for H2O. Now, looking at the Lewis dot structures, we've got two hydrogens, right? So we've got H and H, which are both actually, let me make those the same color. They're both in the first column, so they have one valence electron. Now, oxygen is in the sixth column of the main group, and so it has 6 valence electrons. All right, so let's go ahead and take a look at this Lewis structure for a molecule of water. Now, what needs to take place is hydrogen, as we know, wants to have 2 valence electrons. It wants to be the same as helium. So one hydrogen is going to move in and share its one unpaired electron with one of oxygen's unpaired electrons. All right. The second hydrogen atom will move in and do the same with the second unpaired electron in oxygen's Lewis structure. Now, when you kind of play this blackout game like we did before, if you just look at hydrogen here, it has access to 2 electrons. Same with this hydrogen. It has access to 2 electrons. But now, when you look at oxygen, There we go. Oxygen has access to 8 electrons in this structure, which oxygen wants to have access to 8 because that is the same number of valence electrons that neon has. So here, in this structure, we have met the octet rule, satisfied the octet rule for every atom. All right, so we would then draw the Lewis structure for water as follows. You'd have oxygen, you have your 2 hydrogens, and then, remember, we represent our covalent bonds as lines. You'd have a line from oxygen to 1 hydrogen, then a line from oxygen to another, and that is the covalent Lewis structure for the molecule of water. Now, something that's important to point out, actually, I'm going to do this on another slide. So something that's important to point out here is you'll notice that I drew my Lewis structure of water like this. All right. First, just a little vocabulary. So we would say that here and here, there are 2 covalent bonds. Two covalent bonds. All right. Now here, we would also say that, oh, well, actually, before we get there, we would say that this oxygen is what we call the central atom. Because it is the atom in this Lewis structure that all the other atoms connect to. So it's kind of like the sun of the solar system. It is the central atom. Finally, you'll notice that we have 2 pairs of dots. Each pair of dots, which is a pair of electrons on the central atom, or it could be on other atoms in the molecule, these are called lone pairs. So we would say that we have 2 lone pairs here and here. And this is just short for lone pairs lone pairs of electrons. All right, that is what that stands for. So if you hear me saying, oh, that's a lone pair, 1 lone pair is 2 electrons, just like 1 bond has 2 electrons. And they're just lone pairs of electrons. They're also, they can be called lone pair of electrons. They can also be called non-bonding. Non-bonding electrons is another thing that you'll hear people say. These all refer to the same thing. All right, I just wanted to address those because this is the first Lewis structure that we've drawn, covalent Lewis structure we've drawn with lone pair electrons in them. Wanted to make sure we're all on the same page. The second thing that I want to address is this is how I drew the Lewis structure, but depending upon how you did your Lewis dot structure for oxygen, yours might look different. You may have drawn your Lewis structure for oxygen like so. You could have drawn it like this. Or you could have drawn it like this. Or you could have drawn it like this, for instance. And there's even more ways of drawing the Lewis structure for water. And so yours might look slightly different than mine. You might be wondering, am I wrong? Is his right? And here's a very important thing to stress about Lewis structures is Lewis structures tell you which atoms, or I should say, which atoms are connected, and how they are connected. Oops, not calm. All right, and how they are connected. Lewis structures do not communicate molecular shape. All right, they do not communicate molecular shape. So they tell you which atoms are connected and how they're connected. So for example, looking at these 4 Lewis structures that I've drawn on this page for water, you can see that all of them have oxygen as the central atom, and that oxygen has a single bond to 2 different hydrogens and a lone pair. All right, each one of these communicates that information. And that is all a Lewis structure can communicate. A Lewis structure does not tell you anything about the shape of the water molecule. It just tells you what's connected to what and how they're connected. So it does not matter how you draw the Lewis structure, because Lewis structure never communicates shape. Lewis theory will be augmented by something called Vesper theory, which we'll look at soon. And that will communicate the shape that molecules take. All right, but the Lewis structure by itself does not tell you that. So it doesn't matter how you draw them. All of these are equally valid. Okay. Now, the method that I've been using to kind of draw Lewis structures up to this point has been based off of the Lewis dot structure for each atom, and that might be the way you learn to draw Lewis structures, which is fine. But it's not the only way. It's not the only method of learning to draw Lewis structures. And I would say that in general chemistry, it's actually not quite as streamlined as an approach to drawing Lewis structures as the method that I'm about to teach you. I'm about to teach a different method for drawing Lewis structures. If you've always used the Lewis dot structures for atoms, it's possible to get the correct answers using that method. It's not a problem. But I will say that it's a little more cumbersome. What I'm about to teach you works better in the Gen Chem context. What I will say is if you like to use the Lewis dot structures for atoms, that's actually better for organic chemistry, which if you have to take that, I feel like learning it that way gives you a more kind of, intuitive it gives you a better intuition for how carbon bonds. That being said, though, it's a little bit slow and cumbersome when it comes to general chemistry. And since that is the course that we're taking, I'm going to teach the method that is best suited for what we're about to learn and what we are learning in this course, in this context. So if this is new to you, then it's I think it'll be more advantageous. Obviously, I'm not going to force you to learn it this way because the correct answer, as I like to say, is always correct. But I'm going to give you a method, the blow-by-blow of here's how you draw Lewis structures for covalent compounds. All right. So let's talk about drawing covalent Lewis structures. Oops. Actually, I'm going to do this in blue. All right. So first, the first step when it comes to drawing Lewis structures is step number 1. You want to count your total valence electrons. All right, so you need to total up how many valence electrons you have to spend in the molecule. Step number 2 is select a central atom. Step number 3 is attach all atoms to your central. All right. Step 4, you need to spend, or actually, step 4 should be complete octets. Right, so make sure that the octet rule is is satisfied for each of your atoms. And then step 5 is going to get a slightly different color. Step 5 is going to be assign, oops, I don't want that in blue. Step 5, assign formal charges. Step 6 is you need to make sure you have the best resonance. Best resonance structure. All right. And once you've gone through all 3 of these steps, you will have the Lewis structure for the covalent compound. Now, you'll notice that I put these last 2 in green. We're going to save these last 2 steps for later. All right, we're going to start by just focusing on steps 1 through 4. And once we get comfortable with those, then we'll start working on formal charges and resonance structures. All right, but for now, we're going to focus on, nail down the first 4 steps, and then we will hit up the rest once we kind of establish ourselves there. All right, so let's see. So let's go ahead and put this into practice. Let's go ahead and just work an example. Let's draw the Lewis structure. Draw the Lewis structure for let's do CH4. Let's do the Lewis structure for methane. All right. Well, step number one here is, whoops. Oh, that's ugly. Here, give me 1 sec. Let's just shrink this down a little bit. Step number one is going to be, we need to total our valence electrons. All right, total our valence electrons. Well, to do that, we need to look at how many valence electrons each atom has. And carbon has 4 valence electrons. You can look at the periodic table. It's in the 4th column. Hydrogen only has 1, but because we have 4 of them, we got to multiply that 1 by 4, giving us a total of 8 electrons to spend. Now, something that's worth noting here is when you count your total valence electrons, all right? This is a budget that we have, but it's not like a normal budget, right? A normal budget is, here's the maximum amount you can spend, but if you save money, that's a good thing. Then you have more money. And so, you know, like, for example, my, so I got married a few years ago. And my wife and I, you know, we paid for our wedding ourselves. And so we had a budget, right? The maximum amount we can spend, but, coming in under budget was a good thing for us because, that means we had more money to spend on the honeymoon, right? This is not that. This is not your own hard-earned electrons. These are someone else's electrons. So someone's like, here, have all these electrons. Go crazy. You want to spend all of them. If you don't spend all of it, you don't get any of it afterwards, all right? So that's kind of the mentality. You must spend your full budget of electrons with every Lewis structure that you draw, all right? So that is our budget of electrons. Step number 2, we need to select a central atom. Now, you may be wondering how would you select a central atom? And you always want your central atom to be the atom that can make the most bonds. And another way you can look at that, the atom that can make the most bonds, is by looking at the Lewis dot structure for the atoms in your molecule. Hydrogen has 1 unpaired electron, which tells you something. An atom with 1 unpaired electron usually makes 1 bond. if you compare this to carbon, whose Lewis dot structure has 4, 1, 2, 3, 4 unpaired electrons, carbon likes to make 4 bonds. So because hydrogen, sorry, because carbon likes to make more bonds than hydrogen, we're going to select carbon as our central atom. All right, so carbon's going to be our central atom. We've done step 1, total or valence electrons. Step 2, we've selected our central atom. Step 3, we need to attach all our other atoms to our central atom. All right, now how do we do that? Well, the way you attach atoms together is you got to make a bond, right? So if I'm going to make one bond between my central atom carbon and one of my hydrogens, how many electrons is that going to cost? How many electrons do I need to spend to go into that bond? The answer is anytime you form one bond, it costs 2 electrons. So I need to subtract, when I make that first bond, 2 electrons from my budget. Now I have 6. All right, let's attach another hydrogen. To attach this hydrogen is going to cost me 2 more electrons out of my budget. Now I have 4. Let's attach a third hydrogen, spend another 2 electrons, leaving me with 2. Finally, I've got 2 electrons left in my budget. I have 1 hydrogen left to attach, and I have hit my mark on the nose. There are no more electrons. I've attached all of my atoms to my central. So I have done steps 1, 2, and 3. Now I'm on step 4. All right, we need to make sure that every element in this molecule has a completed octet. To do that, we need to zero in on each element individually. All right, wait here, hang on. There we go. All right. A little sloppy, but it'll get the job done. So if I look at this hydrogen, how many electrons does it have access to? The answer is it has access to 2 electrons. It's happy. If we move our blackout page thing over and ask about this hydrogen, how many electrons does it have? Well, this guy has access to the 2 electrons in that bond, so it has access to 2 valence electrons. It's content. What about this hydrogen over here? Well, this hydrogen has access to the 2 electrons in that bond, so its octet rule is satisfied. What about our 4th hydrogen? This 4th hydrogen down here has access to the 2 electrons in its bond, so its octet rule is satisfied. Oh, Kate. You are so totally welcome. All right, now let's look at, there's one last atom we've got to consider, right? It's the one in the middle. How does carbon feel about the Lewis structure it finds itself in? Well, if we look at carbon in isolation of all the other atoms in this molecule, how many electrons does carbon have access to? The answer is, well, it has 4 bonds around it. It has access to all the electrons in each bond. There's 2 electrons in each bond, right? So carbon in this molecule has access to 8 electrons, which means that it too has a full octet. So, whoops. Oh, lame. Here, let me redraw that over here. Eight electrons. So every element in this molecule has a complete octet, which means that our job is done here. This is the Lewis structure for CH4. That is the answer. All right. That is a covalent Lewis structure for methane. Let's see, what time is it? Okay, let's do a few more examples. Let's draw the Lewis structure for, again, we're starting slow here. Let's do the Lewis structure for ammonia, NH3. All right, now, first, we got to start by counting up the total valence electrons in our molecule. Nitrogen, if you look at the periodic table, has 5 valence electrons. Hydrogen only has 1, but we have 3 hydrogens in this molecule. So we multiply that 1 by 3, and again, we have a total of 8 valence electrons in our budget to construct our Lewis structure. Let's take a look now at our central atom. All right, we need to construct our central atom. Or, sorry, not construct, select our central atom. We know that we want to select the atom that can make the most bonds. Hydrogen, because it has 1 unpaired electron, likes to have 1 bond. It doesn't, again, this is a preference. Not every element will always have bonds equal to the number of unpaired electrons, but as kind of a rule of thumb, it's pretty reliable. Nitrogen has 3 unpaired electrons, which tells us that it normally likes to have 3 bonds. So we're going to select nitrogen as our central atom. All right, so we put nitrogen in the middle. We've handled step 1, step 2. Now we need to attach all other atoms to our central. So we have here these 3 hydrogens that we need to attach to nitrogen. And at this point, we kind of know how this goes, right? We know that hydrogen will want to make a bond with nitrogen, right? We got to attach it. And we got to do this 3 times, right? To attach all our central atoms to, all of our other atoms to our central. It's going to take 2 electrons a pop. With 3 nitrogens, that means we're going to need to spend 6 electrons out of our budget of 8, right? To attach them all, to attach all the hydrogens to our central atom, nitrogen. But now what do we do with the remaining 2 electrons? All right, we've completed step 3, attach all atoms to our central. Now we're on step 4. We have to complete our octets. We got to complete our octets, and we have to have 0 electrons in our budget when we're done. You must use all of them. Now you'll notice that for every hydrogen atom in this molecule, it's got 2 electrons, which means it's happy, right? It has the same electron configuration as neon. So hydrogen has all of its needs met. Right now, nitrogen has access to 3 bonds. So it has access to 3 times 2, which is 6 electrons. This is not okay. Nitrogen does not have its octet rule met. But look at what we have. 2 electrons in our budget. What you need to do is take those 2 electrons that you have left in your budget, spend them, and give them to nitrogen as a lone pair. Now, nitrogen, whoops, actually, take that back. Nitrogen has 6 electrons in the form of bonds. Oh, hang on, sorry. Oh man, okay. Sorry. There we go. So we're still doing all that. We're taking our 2 electrons and we're giving them to nitrogen as a lone pair. So nitrogen still has access to the 6 electrons in those 3 bonds, but now it also has the 2 electrons in its lone pair, which adds together to 8, right? 8 valence electrons. So at this moment in time, now every atom in this Lewis structure has 8 valence electrons, and a full octet. All right, so we got step 4 completed. This is the Lewis structure for NH3. All right, now I want to take things up a notch. And do an example that's next level difficulty. Let's take a look at O2. Let's draw the Lewis structure. Now, step number 1, right? We need to total our electrons. Oxygen has 6 valence electrons, if you look at the periodic table. We've got 2 oxygen atoms, so our total electron budget is 12. All right, we've handled step number 1. You can't really pick a central atom when you only have 2 atoms in your molecule, because the term central atom is meaningless, more or less, right? There's no atom in the center. We're just attaching these 2 together. So let's do step 3. Let's attach all of our atoms. Done and done. We had to spend 2 electrons in our budget to attach these 2 together. Sorry, I'm having a hard time with words today. Leaving us with 10 electrons, and that brings us to step 4, where we need to complete our octets. Now we're going to do the same thing that we did with the previous example, right, with nitrogen, where we've attached everything. Now we got to complete our octets. You'll notice that this oxygen right here has access to 2 electrons, but we got to have a full octet, right? It needs 8. So we're going to spend 6 electrons from our budget so we can give it 1, 2, 3, 4, 5, 6, and then the 2 in the bond, 7, 8. So now, whoops, hang on. So now we have 6 plus 8, no, 6, 2, oh my gosh, okay, hang on. 2 electrons plus 6 electrons is 8 electrons. There we go. Now let's look at our other oxygen right here. It has 2 electrons, which is great. For it to have a complete octet rule, we need to add 6, but here's where you need to be careful, because you'll notice that there are only 4 electrons left in the budget. So after you give oxygen all the remaining electrons that you have to spend, right now we have none, you'll notice that we have 2 electrons in the bond plus 4 in lone pairs. Right now, there's only 6 electrons around this oxygen, which is not okay, all right? If your Lewis structure that you've drawn violates the octet rule, it's incorrect. It's going to get a 0, all right? So you must satisfy the octet rule every single time. Now, you may be looking at this and going, Josh, this looks like an impossible problem because we're out of electrons. We don't have any more electrons to give. How do you solve this problem? All right? This is going to happen to you over and over and over again. You're going to run into a situation where it's going to seem like you're like, if only I had 2 more electrons, I am missing two electrons. And you'll notice I put that in quotes, right? The electrons aren't missing, but it's going to feel like you are. When you feel that feeling like I'm missing 2 electrons, here's how you solve it, all right? What you do is you take 2 electrons from an atom that has all the electrons it needs, that has a full octet. And, whoops, sorry about that. You take them and you use them, you share those electrons with the atom in need. So you take the atom whose needs are met, and you take those electrons and you share them with the other atom, all right? What does this do? How do you share electrons? I'm so glad you asked. Well, turns out we're already sharing the 2 green electrons, right? That's called a bond. So if you take 2 electrons from the oxygen on the right and share them with the oxygen that's on the left, it's just going to look like a second bond is there. Now, when you look at the number of electrons that this oxygen has on the right, it has 2 electrons plus the 2 electrons that it's sharing in the second bond, plus 4 electrons in the lone pair. And when you look at this oxygen, oops, I wanted that to be green. When you look at this oxygen, it's got 2 electrons from the first bond, plus 2 electrons from the second bond, plus 4 electrons from its lone pairs. And you can see now that both oxygens in the Lewis structure as drawn have access to 8 electrons, which means we can finally say mission accomplished. We have completed all the octets in this molecule. All right, I realize we're a minute over. We're going to wrap up. I just want to say one thing. So, two things actually. So this Lewis structure, this is a new type of covalent bond where so when there's one line, it's one bond. 2 lines, this is called a double bond. all right? This is called a double bond. And just like one single bond has 2 electrons, a double bond has twice as many. So there are 4 electrons at play in this double bond. All right. Now, at this moment in time, you have enough knowledge to tackle several examples of Lewis structures. And I want to leave you with some to try. Again, Wednesday is Veterans Day, November the 11th. So we won't be streaming, so I'll catch you guys all on Monday. But here's a few for you to practice in your own time, and we'll do these together as well. So try to draw the Lewis structures for, take a shot at N2. Take a shot at C, H, H3, Cl. Take a shot at C2H. No, not that one. CH2O. Okay. Sorry. I see your question. Hang on one second. And then maybe one last one to try. Try C2H2. That one will be a special challenge. So see if you can take a crack at, oops. Oh, goodness. Oh, wow. Sometimes Photoshop decides to be really special. Give these a try on your own. We'll come back and we'll do them on Monday. Hit me up in office hours if you can't wait that long. And we'll continue with Lewis structures. And on Monday, we'll get to our last 2 rules, which for now you can ignore for these structures. All right. That is a great question. The question is, do double bonds take double the energy to break? And the answer to that question is actually no. All right. It does not take double the energy to break for reasons that we'll get into a little bit later. I'm not sure if it's going to be this chapter or the following chapter. But one of the things you see is when you look at bond energies, the energy for a carbon-carbon single bond versus a carbon-carbon double bond, the double bond does not double the energy. It's larger than a single bond, so double bonds take more energy than single bonds to break. But it's not doubled. And the reason why, and this is what we'll get into when we get into our discussion of hybridization, is that a single bond is made up of what's known as a sigma bond. It's this particular type of bond where the electrons are held kind of in between 2 nuclei. But a double bond is made up of a sigma bond layered beneath a pi bond. And with a pi bond, the electrons float above and below the 2 nuclei, and they're not as stable as the sigma, which is sandwiched between. So the second bond is a different type of bond, and that type of bond, the pi bond, is weaker than the sigma bond. And so when you have a double, it's not double the energy because it's 2 different types of bonds forming. Again, we'll get to that when we discuss hybridization, which might be at the end of next week, but most likely will be the week following. So anyways, excellent question. I don't want to say your handle out loud because it sounds like I'd be insulting you. But the tutor who asked that question, thank you. That was an excellent one. And we'll get to the reason why they're not doubled once we hit hybridization. All right. That is it for lecture today. Thanks for hanging out. We went a little bit over. I'll catch some of you in office hours tonight, and the rest next week, because we have Veterans Day this week. Alrighty.